О, смотрите, она все понимает, слушает меня. Вот, понятно, так. Ну вот у нас Тимур Ойхберг, профессор Ойхберг университета Иллиной, кажется, если я правильно.
Именно так, да.
Штат Урбана, кажется. Не штат Урбана, а там город Урбана.
Город Урбан. Ну,
Город
поселок городского типа.
Поселок городского типа. Хорошо. Ну вот, значит, чтобы не забыть, следующий докладчик, это уже вроде в обычные 6 часов, это будет Федор Коган, но сейчас он где-то находится тоже в Штатах, а то и в Торонто, или в Торонто
В Торонто.
В Торонто он находится. Ну вот, тем не менее, он, значит, видимо, рано проснется, или я уж не знаю, что он сделает, и доклад будет наш состоится в 6 часов. Ну, а теперь я с удовольствием представляю слово Тимуру. Пожалуйста.
Окей.
Время, как обычно, Тимур, время по желанию докладчика от часу до полутора. Ну, можно даже меньше, если человек считает, что он все сказал. Вот. Ну, а можно, в общем-то, и больше, если человек считает, что он еще не все сказал. Ну, вот теперь все, я умолкаю, пожалуйста.
Но я не думаю, что будет больше, но если вы не возражаете, я переключусь на английский, потому что по-русски как-то у меня словарный запас на эту тему весьма слаб.
Ну, тем лучше, тем лучше. Давайте. А мы будем учиться у вас словарному запасу. Пожалуйста.
Хорошо. Ну, so today's topic is stable phase retrieval, and this is a joint work with my excellent collaborators, with Dan Freeman from St. Louis, and with Ben Pineau and Mitchell Taylor, who are currently at Berkeley. Mitchell Taylor, by the way, is going to Switzerland next year, but well, I don't know what Ben is going to do. Well, I try to make this. By the way, I should also say that I really appreciate you coming in this unusual time, and I try to make this talk maybe more entertaining than otherwise. And I would like to start with the picture of this elegant gentleman, who is none other but Max von Laue, who won a Nobel Prize in Physics in 1914, and he did so for determining crystal structure of crystals by studying the diffraction of X-rays on crystals, and X-rays, of course, had been discovered maybe a couple of decades before that. So this is one of his photographs. This apparently shows the destruction of X-rays on salt, on the crystal of table salt. And well, I guess he had to do a lot. He had to go through a lot of effort, building all the machinery, and apparently, so here I'm not 100% certain of what's going on, but apparently the mathematical side of the problem he was trying to solve was the following. So he had to determine or recover a certain function phi, and the diffraction of X-rays gives you its Fourier transform, denoted by phi hat. And so if you try to scatter visual light on something, then it's also the same apparent process. So once again, I don't know exactly how this scattering does Fourier transformation, but the point is that with visual light, somehow your eye manages to take the inverse transform, and then you kind of recover the shape of the object you are looking at. For X-rays, you don't have your eyes, you don't have, like the usual lenses made of glass or plastic will not work on X-rays. X-rays have too short of wavelengths. So you project them on the screen, and on the screen you somehow measure, you see the intensity of the diffracted wave. So you actually perceive the Fourier transform itself, but you perceive the absolute value, which corresponds to the intensity of the diffracted wave. So somehow, knowing the absolute value of this Fourier transform, you have to recover the original function phi, or maybe phi hat, whichever you want. And hopefully also this recovery is not too sensitive to errors. And this is here of course you have to understand, you have to note that first of all, if you look at this phi, well, I try to kind of circle it with my pointer. I don't know whether you see the pointer or not. So if you look at this phi, well, if you multiply it by something unimodular, by some unimodular scalar, this will not change the modulus of phi of the modulus. If you multiply the phi hat by unimodular scalars, this will not change the modulus. So you recover phi hat up to unimodular scalar. Really, this is the phase. So this is the ratio of phi hat to its modulus, to its absolute value. And of course, also this problem, you cannot just solve it in general. You have to impose certain constraints on what phi hat or phi, or whichever, once again, you want to work with. Which you need to impose some constraints. And I think in the original question, these constraints were coming from some physical reality. Now, once mathematicians get a question from physicists, what mathematicians do, they generalize, or we generalize it until the original question is no longer recognizable. So in our case, we were trying to generalize it by replacing space of square integrable functions by an arbitrary Banach lattice. And the constraint we are working with is a membership of in a subspace of a Banach lattice. So by a subspace, well, from what I understand, this constraint on membership in a subspace is somehow natural from the standpoint of approximation theory, and also it makes somewhat easier to answer the questions in front of us. Before proceeding, let me briefly remind you what a Banach lattice is. So a Banach lattice, well, it's a Banach space. It's equipped with a certain partial order, and this partial order is consistent with addition and multiplication by positive scalars. By the way, here I'm talking about a real Banach lattice. I will get to the complex setting in a moment. What is important, what really sets Banach lattices apart from general ordered spaces is that you can define the maximum and the maximum, the least upper bound or the minimum, the greatest lower bound, which are denoted by the meet and the join respectively. And finally, the norm is consistent with the order. So if the modulus of x does not exceed the modulus of y, then the norm of x does not exceed the norm of y. And the modulus is what you intuitively think it is. It's defined as the maximum of x and its opposite. So we also need the notion of disjointness. So two elements are disjoint if the minimum of the moduli is 0. And in a sense, a way of visualizing a Banach lattice is to think of a space of functions, such as LP or C of K. And in this case, the operations are just the usual pointwise operations. So most of the time in this talk, I'll be speaking about real lattices. Sometimes I also mention the complex ones. And there are several approaches to defining a complex lattice, but the one that I take is fairly simplistic. Basically, I start with a real lattice and complexify it. And on the on the real lattice, you have all those lattice operations that I have just mentioned. On a complex lattice, the important thing is that we are able to define the modulus. So when we do so, we take a pair x plus iota y. So iota is, as usual, the imaginary unit. X and y are elements of the real lattice we are complexifying. And then we define the modulus as the supremum of things like cosine theta x plus sine theta y. So here I wrote, let me maybe try to change something a little. So let me change the method of showing this. Hopefully this will permit me to, I was kind of hoping to be able to underline things, but apparently I can't. So in any event, so here I'm taking the maximum and the maximum of a certain compact set in the real part of the lattice. And since the set is compact, the maximum exists. So I'm not cheating here. And then I'm defining the norm on this complexification. So for any pair x plus iota y, I define the norm of the modulus. And a complex Banach lattice is just a complexification of a real lattice. And the usual examples are, once again, function spaces such as T of k spaces or LP spaces. If you go through this complexification process, you get precisely the same LP that we know and love, or maybe just know. I know that some of those present are more familiar with or more used to working with sister algebras. So a sister algebra is a Banach lattice if and only if it is commutative, because otherwise, if you look at the real part, you may not be able to take maxima and minima. So even on two-dimensional two-dimensional self-adjoint matrices, it's not very difficult to come up with examples of pairs where no maximum can be defined, no least upper bound can be defined. So having described what a Banach lattice is, let me define phase retrieval and stable phase retrieval. So our setup is this: X is a Banach lattice. A subspace E of this Banach lattice is set to do a phase retrieval, which we refer to PR if for any elements f and g from this E, the moduli are equal if and only if one of them is a unimodular scalar multiple of the other. And so in other words, knowing the modulus, we can retrieve the element f itself. We say that it does stable phase, C stable phase retrieval, where C is certain positive constant, if for any f and g, if the moduli of f and g are small, then f and g are kind of close to each other. Well, except that here too you have to take into account multiplication by a unimodular scalar. And here I'm working in both real and the complex case. In fact, real case will be more common. So in the complex case, of course, you take the infimum over all those lambdas. It's just a unit torus. But in the real case, this is just this infimum. It's just a minimum of those two, of the minimum between f minus g and f plus g. Now, from the definition, you see that stable phase retrieval and well, I forgot to put it on the slide, but we shall say that a subspace E does stable phase retrieval, or SPR, if it does C stable phase retrieval for some value of C. And stable phase retrieval is clearly stronger than phase retrieval, and in fact, it is strictly stronger because it can be shown that any infinite dimensional, well, so here I wrote infinite dimensional real Banach lattice, but I'm certain that this construction works in the complex case as well. So any real Banach lattice contains a subspace which does phase retrieval, but not stable phase retrieval. So stable phase retrieval is definitely stronger than the regular phase retrieval. Now there is maybe a slightly different way of looking at this problem. So here I'm reminding the definition of phase retrieval and C-stable phase retrieval. So we can split our Banach lattice into equivalence classes. Specifically, we can say that f is equivalent to g if it is a unimodular scalar multiple of g. And well, this square brackets around f will denote the corresponding equivalence class. So then we naturally have a map capital phi from the set of equivalence classes to the positive cone of x. And phase retrieval just tells us that if you restrict this map phi onto the equivalence classes coming from E, then this map will be invertible. And stable phase retrieval is giving us something more. Namely, we can on this quotient topological space, well, we can define the distance, which is inherited actually from X itself. So this is the distance between two equivalence classes. And on X plus, of course, we have the usual metric inherited from X. So the map phi is contractive, and C stable phase retrieval just means that the restriction of phi to the equivalence classes of A has a C Lipschitz inverse. Now this condition of having this Lipschitz inverse is in a sense not very convenient to check, not very convenient to verify, because it may, if you look for violations of this condition, it may happen that you can only find the violation when f and g are far out, they have large norms, but the distance between the moduli is fairly small. So this presents a serious obstacle, but later we shall see that we can go, that there is a way around it. So let me again recall those definitions. So I promise this is for now, this is at least the last slide which shows those definitions. So we'll get to maybe more interesting stuff in a moment. But here I just want to say that, of course, there are many different, you can ask, like, in a sense, in this talk so far, I'm mentioning only two conditions on this map phi. So one condition is that it is invertible. Another condition is that this map has a Lipschitz inverse. So of course, in theory, there may be some other things between invertibility and having Lipschitz inverse. Well, it turns out that in a sense, having Lipschitz inverse may be a natural requirement because it turns out that if this map phi has uniformly continuous inverse, then the inverse is actually Lipschitz. In other words, the subspace E of our Banach lattice does stable phase retrieval. This, I didn't call it even a proposition. This is more like an observation. And the proof is fairly straightforward because if we have a uniformly continuous inverse, then just recall the epsilon delta definition, which first-year students are supposed to know. So in particular, if you apply it with epsilon equal to 1, then you see that for any delta, that there exists a positive delta, so that if the moduli of f and g differ by less than delta, then the distance between the corresponding equivalence classes is no more than 1. And then you just use scaling and say, okay, so if f for general f and g, then the distance between the equivalence classes is no more than delta to the power -1 times the distance between the moduli. So, okay, so this was maybe boring stuff. And then we want to maybe look at some examples. We want to look at subspaces of Banach lattices which have phase retrieval or stable phase retrieval, and also those which don't. And our first question is that what kind of obstacles do we have for phase retrieval? And one obvious obstacle is disjointness. So let's say we have a subspace E. So here I wrote that it's inside of LP, but really inside of any X, inside of any Banach lattice X, this will work as well. Let's say F and G. Let's say F and G are two disjointly supported functions in E. So here, say F is in blue, G is in red. So then, on the one hand, F plus G is not a multiple of F minus G. But on the other hand, the moduli are the same. So what is the moral of the story? The moral of the story is that if we have two disjointly supported functions in a subspace E, then this E cannot possibly do phase retrieval. So it turns out that, well, if you want to do stable phase retrieval, you have to bar not just disjointness, but something stronger, which we call almost disjointness. And then it will turn out this almost disjointness turns out to be, in the real case, the only obstacle to stable phase retrieval. So here are the definitions. So first of all, notation-wise, we use this S of E to denote the unit sphere of E. And we say that the subspace E over Banach lattice X contains almost disjoint pairs if for every positive epsilon we can find F and G in the unit sphere so that the minimum of the moduli has norm less than epsilon. So I remind you that in the definition of disjointness, this modulus is 0. So almost disjointness, which means that modulus is almost 0. And it turns out that a subspace E of a real Banach lattice does stable phase retrieval if and only if E contains no almost disjoint pairs. This is a qualitative result. There are also quantifications of this, but I'm not going to touch on this here. So the proof is kind of surprisingly technically involved. So one direction is kind of straightforward, because if you have almost disjoint pairs, then essentially redrawing this picture from the previous slide, which still should be visible, redrawing this picture, you see that if you have almost disjoint pairs, then stable phase retrieval cannot possibly occur. But the opposite direction is harder, and here you, I mean, I was kind of hoping for an easier proof, but we haven't been able to find it yet. So instead, what we do, it's kind of it's a fairly well-known fact that every real Banach lattice can be embedded into an L infinity direct sum of sufficiently many copies of L1, and this reduces the problem to actually work in an individual L1s, and somehow in L1 there is enough structure to show that if there are no almost disjoint pairs, then you do have phase retrieval or stable phase retrieval. So here I was stressing that this theorem only works for real Banach lattices. So by the way, here on the new slide, I'm repeating the definition and the statement of the theorem. And I should also say that we don't yet fully understand what's going on in the complex setting. So in the complex setting, we know that there exists at least one more abstraction, namely that if we have a subspace E of a complex Banach lattice, which contains two linearly independent real vectors, then this E must fail phase retrieval. And why? Because, well, if F and G are those vectors, then if you take F plus iota G and F minus iota G, then the moduli are the same, but one is not a scalar multiple of the other. So phase retrieval cannot cannot occur. And for this, as an example, you can see what happens in just the three-dimensional space when F is when you have this F and G, and their span, which we denote by E, will have no almost disjoint pairs, but phase retrieval will fail. So there is at least this abstraction, but there are actually more, at least minor things. So the complex in the real setting, we have this powerful tool of almost disjointness. For the complex setting, this will not work. Well, I mean, this will work, but this is that we need more tools which we have not devised yet. This technique with almost disjoint pairs allows us at least to find examples of subspaces which do stable phase retrieval. So one may be fairly straightforward example is the following. So let's say we have F1, F2, etc. is a sequence of independent standard normal random variables And it turns out that we can represent them as functions on, say, the interval from 0 to 1. So we take their closed span, and it turns out that, well, the subspace E will do stable phase retrieval in LPs for all p's between 1 and infinity. Infinity, of course, not included. And so I've stated this proposition without specifying the field of scalars. So it turns out that this will be true both in the real and the complex case. But let me present the real proof only. So this is actually a very nice property of Gaussian random variables that, well, the linear combinations are again Gaussian. So all the if you look at the unit sphere of A, then any element there will be a standard normal random variable. And well, we can find a positive alpha so that the probability of the standard, well, so here lambda is a Lebesgue measure. You can interpret it as a probability. So the probability that the absolute value of H is greater than this alpha is at least 3/4. So in other words, alpha is so small, then the probability of the standard normal random variable being less than alpha is no more than 1/4. But now let's say F and G are two elements of the unit sphere. So what is the probability that both of them are greater than alpha? Well, the probability that each of, or maybe I should have said greater or equal than alpha. Well, what is the probability that each of them is less than alpha? Well, this is 1/4 for each of them. So therefore, the probability that both of them are at least alpha, this is at least 1/2. And therefore, the minimum of F and G, or the minimum of the moduli of F and G, is at least alpha over 2. So I don't really care what alpha is. The only thing that I care about is that no matter what F and G from the unit sphere of E I take, the norm of the minimum of the moduli is that large. So this means that E has no almost disjoint pairs, and therefore it does stable phase retrieval. Now, in this brief proof, I did not use, in fact, that I'm working in LP. So instead of LP, I could have worked in any rearrangement invariant space on 0, 1. So for instance, I could have, well, except that of course, my space had to contain had to contain Gaussian random variables. So any Lorentz space, so the same proof will actually work in any Lorentz space as well. Now I said that this proposition also holds in the complex case. Well, it does, but as I said, in the complex case, in the complex setting, the absence of almost disjoint pairs is not sufficient to guarantee stable phase retrieval. So in the complex setting, a different proof is required. And I think in the complex setting, we can only handle LPs. We cannot handle more general rearrangement invariant spaces. And also, I didn't really use very strongly the assumption that I'm working with Gaussian random variables. The only instance when this was used is when I said that anything on the unit sphere is a standard normal random variable. So everything on the unit sphere has the same distribution. And then also that the probability of being near 0 is small. And it turns out that instead of standard normal, you can also work with with the so-called R-stable random variables. So I'm not going to define what they are, but this is one of the favorite toys of people in function analysis. And they span little lr in LP when R is less than 2 and P is between 1 and R. So, so the original proposition gave us an SPR copy of the Hilbert space inside of LP. And this last remark on the bottom of the screen gives us a copy of little lr inside of LP, an SPR copy of little lr inside of LP. So we shall see later that these are kind of archetypical examples, and we cannot really get anything significantly better than this. So how do we know this, or how can we suspect this? So almost disjoint pairs haven't been studied much, as far as I understand, but almost disjoint sequences have been studied. So here we say that the sequence Fn in the Banach lattice is almost disjoint if it is if you can approximate it by a disjoint sequence. So approximate meaning that the pairwise distances go to 0. And a subspace of a Banach lattice is dispersed if it contains no almost disjoint sequences. And around 1960, Kaditz and Pelchinsky established this important dichotomy. So for a closed subspace of capital LP, so LP here is, well, P is between 1 and infinity. As far as I understand, a similar thing happened for P less than 1, but I'm not going to touch that. So for a closed subspace E of LP, the following are equivalent. So the first statement is that E is dispersed, meaning that it has no almost disjoint sequences. The second statement is that for any Q between 1 and P, the Q and the P norms on E are equivalent. The third statement is that there exists a Q so that the Q norm and the P norms are equivalent. And well, I didn't put it here, but these are also equivalent to the LP norm is not the LP norm, but the norm topology from LP is equivalent to the measure topology. And actually for P different from 2, these conditions are equivalent to the subspace E not containing little LP. And kind of this makes things maybe a little clearer intuitively, because kind of what is a natural way of putting little LP inside of a capital LP? Well, you just take a bunch of disjoint elements. So this dichotomy, in a sense, among other things, tells us that this is kind of the prototypical way of containing little LP. So if you have little LP, then you can discover almost disjoint sequence. And if you don't have little LP, then somehow all the vectors of E are fairly spread out, and the measure topology is equivalent to the norm topology. So how is it important to us? Well, well, let me also remind you another theorem. So let's suppose that E is a dispersed subspace of LP. So if P is 2 or greater, then E is isomorphic to a Hilbert space. So this part was once again established by Kaditz and Pelchinsky in around 1960. For P between 1 and 2, the situation is different. And namely, in this situation, we can only say that E embeds into LQ for for some q between p and 2, and this was due to Haskell-Rosenthal in the early 1970s. And here I should remind you that why are we interested in all this business? Because we know that SPR subspaces are dispersed. So all these statements are true about SPR subspaces as well. So maybe going back to this to this theorem of that is now on the screen. Well, it turns out that it cannot be improved. So the question is, so first of all, well, so let me actually state this proposition. So let's suppose that either of two situations is true. So either P is between 2 and infinity and Q is 2, or P is between 1 and 2 and Q is between P and 2. And in this situation, LP contains an SPR subspace which is isometric to LQ. So here I should say that this result is in a sense optimal, because in what situations does LP contain LQ at all? So LP contains LQ. Well, it may happen, of course, that Q is the same as P, or the relation between P and Q is precisely as in this proposition. And of course, if P is the same as Q, then you have little LP inside there, and you therefore have almost disjoint sequences, and stable phase retrieval will not be possible. So this is as far as the stable phase retrieval goes, this is really the best we can hope for. So I'm not claiming that any copy of LQ inside of LP will do stable phase retrieval, but there are copies of LQ inside of LP which do that. From this, we can actually state the following. So a Banach space E admits an isomorphic SPR embedding into LP in one of the following two situations. So here there is a typo. Either P is between 1 and 2. It's not infinity. It's 2 here, and D embeds into LQ, or P between 2 and infinity, and D embeds, and D rather is isomorphic to a Hilbert space. So these are Banach spaces which can be embedded into LP01 in an SPR manner. This topic about the connection between SPR and between SPR and being dispersed is it I think merits a couple more slides. So I remind you again that dispersed means the absence of almost disjoint sequences. So of course there are dispersed subspaces which fail to do SPR, because you can just take two dispersed subspaces, take their direct sum, and now this direct sum maybe I can, oh, never mind. Come on. It's doing something that I didn't intend. So this direct sum will obviously have disjoint pairs, and therefore SPR cannot happen. However, it turns out that being dispersed does not imply SPR. However, it almost does. So it turns out that any dispersed subspace of LP has a further SPR subspace. And here I forgot to say that, well, I should say that to make this statement interesting, I should have said that any infinite dimensional dispersed subspace of LP has a further infinite dimensional SPR subspace. And once again, the role of LP is not really essential here, and LP can be why am I doing this to me? Yeah, this is fine. So LP can be replaced by any order continuous Banach ambient lattice X. So order continuous means that if we have a net which decreases towards zero, meaning that there is nothing positive smaller than this net, then the norms go to zero as well. So as an example, we know that any reflexive Banach lattice is order continuous, and L1 is order continuous as well. And the proof really strongly uses order continuity, and we don't know whether the result holds without it. So let me also mention a few more things about this relation between SPR and containing and being dispersed. So here I'm reminding you again of the Kazets-Pelchinski dichotomy. Also, I'm quoting this result of Rosenthal. Well, no, I'm not quoting that. I'm just trying to rephrase what's coming from Kazets-Pelchinski. So let's suppose that E is a dispersed subspace of LP. So then, and we are assuming so E is closed, since the norms of LQs are equivalent to the LP norm for Q less than P, then we conclude that E is also closed and dispersed subspace of LQ for all Qs less than P. So now, what assumes that E does SPR, does stable phase retrieval in LP. So from this, we conclude that it's dispersed in LP. From this, we conclude that it is dispersed in LQ, once again, for Q less than P. So the question is, does E also do stable phase retrieval in LQ? So in other words, does stable phase retrieval pass downwards on the scale? And the answer is that sometimes yes, sometimes no. So let me get first to the no part. So there exists, so if P is greater or equal than 2, then you can find the subspace of LP, which does SPR in LP, but not in LQ for any Q less than P. So here is once again the statement of this theorem. However, for P less than 2, the situation is strikingly different. Namely, if you start with an SPR subspace of LP for P less than 2, then the stable phase retrieval property will pass down to all the, and it will do stable phase retrieval in LQ for all the Qs between 1 and P. And even for general P, we can do some kind of extrapolation of stable phase retrieval. Namely, we have the following theorem. So let's say we have Q and P, and Q is strictly less than P. Let's say E does stable phase retrieval in LQ, and the P norm is equivalent to Q norm. So note that here P is greater than Q. So this equivalence of two norms is not at all guaranteed. So this is actually an extra assumption. Then it turns out that E does stable phase retrieval in LR for any R between 1 and P. So if we know about stable phase retrieval in Q, and if the norm on some P greater than Q is equivalent, then we can still extrapolate stable phase retrieval. So let me. I see that I'm already 50 minutes into the talk, and I know that you have a lot of patience, but I have to go and pick up my in-laws at the airport at some point, and they may not have as much patience as you do.
We have not only patience, we have an interest as well.
Pardon?
We have not only patience, but interest.
Okay, thank you for saying this. So I'm not going to be in an undue hurry anyway, but so I may still skip a few finer points. So here is again this definition of C-stable phase retrieval. So once again, I have this equivalence classes. So the equivalence class is determined by multiplications by a unimodular scalar, doing C-stable phase retrieval corresponds to this map phi having C Lipschitz inverse. So it turns out that you don't have to check this C Lipschitz inverse on the whole space E. Rather, you only need to do this on the ball, and not just on the whole ball, but only on the pairs of elements of the ball, which are neatly separated from each other. So first of all, let me quote maybe a technical result, which is I call it technical, but it's extremely important actually. And this result, well, it's kind of maybe a little bit hard to read, but let's say you have, so the idea is the following, that let's say F and G are elements of E, and kind of an interesting situation is that F and G witness the failure of C-stable phase retrieval. For those F and G, you can find further F prime and G prime, so that the distance between the moduli is no more than the distance between the moduli of F and G. But on the other hand, the equivalence classes of F prime and G prime are well up to a constant, at least as far away from each other as the equivalence classes of F and G. But also, we control the norms of F prime and G prime. So F prime and G prime, in a sense, well, maybe up to a constant, are as far away from each other as they can possibly be, because the norms are somehow not large compared to the distance between the two equivalence classes. And the proof is fairly long, but the idea is that you look at this E, you equip it with the appropriate Hilbert space norm, and then you somehow transform those F and G. You can somehow move them like in an opening motion to get to the point when they are orthogonal, and then somehow orthogonality is what gives you the right result. And this actually explains where the root 2 comes from. It comes from John's theorem, which tells us that the distance of any Hilbert, the Banach-Mazur distance of any two-dimensional space to the Hilbert space is at most root 2. And the important corollary of this theorem is the following, that let's suppose that well, we are still in the same setting, that T is a subspace of Banach space X. And let's suppose that whenever U and V are in the unit ball, and the distance between the equivalence classes is at least 1 over root 2, so they are kind of on the opposite ends of the unit ball in some sense, then the distance between the moduli is at least the distance between the equivalence classes over K. Then it turns out that E does stable phase retrieval with this constant root 2 times K. So at the price of, in a sense, of adding this root 2 to the constant, you reduce your problem to checking for stable phase retrieval on well-separated points in the unit ball. So the proof is kind of not very interesting, so I'll skip that. And instead, let me just restate this corollary. Well, as I said, this works. Maybe I forgot to say this, but we'll say it now. It works both in the real and the complex case. And it turns out that this corollary has plenty of consequences of its own. So one of them is a proposition. So in the finite dimensional case, in the finite dimensional setting, stable phase retrieval is equivalent to phase retrieval. So as I said at the beginning of the lecture, stable phase retrieval always implies phase retrieval, but the converse is in general false for infinite dimensional spaces. For the finite dimensional spaces, the converse implication also holds. And the idea of the proof is just to run the compactness argument. So basically, if E is finite dimensional, you look at the pairs of points in the ball, which are separated from each other. And of course, compactness argument is just something that arises naturally in this setting. There are also maybe some more complicated examples. So this one is actually not due to me, or not it does not, it appears in the paper of two of my co-authors, Ben Pineau and Mitchell Taylor, with Michael Christ. All three of them are from Berkeley. So the setup is the following. So let's say mu is a probability measure. Q is some number greater than 4. And let's say we have a sequence Rn in Lq sequence of mean 0, identical independently distributed random variables. You look at their span in it's at the span of these variables in L2. Well, it turns out that the span does stable phase retrieval if and only if the modulus of Rn is not identically constant. So again, this works both in the real and the complex setting. Once again, I'm not going to give the proof, just maybe the idea. So one direction is fairly straightforward, because of course, if Rn has constant modulus, then even the phase retrieval will fail. Stable phase retrieval will definitely fail. However, if it's not constant, then what they did initially, they established what they call the Hölder phase retrieval. So they showed that for any f and g in E, well, the distance between the equivalence classes is bounded above by this expression on the right. Gamma is here some number between 0 and 1. Well, what is the difference between the Hölder phase retrieval and the stable phase retrieval that I've been talking about over the last hour? Well, in the stable phase retrieval, it's just a particular case of when gamma is equal to 1. Well, so they establish and establishing this Hölder phase retrieval, it requires it's not at all trivial. It requires a lot of kind of hard analysis work, where you calculate this norm and you calculate that norm, and then you somehow show that these two norms are equivalent, and well, the Hölder phase retrieval was their end result. But then you just once again restricting your attention to the well-separated points of the unit ball, you see that, well, this kind of a condition holds, and therefore, so you can check for stable phase retrieval on those separated pieces of the unit ball, and therefore you have phase retrieval and a stable phase retrieval, maybe with a different constant. So this is another example. Now maybe now I want to move from LP spaces to C of K spaces, and here I want to work in the real setting. So what do we, and once again, as usual, K will be a compact Hausdorff topological space. First of all, well, we know that C01 or C delta contains all separable Banach spaces. Well, it turns out that those embedding can also do stable phase retrieval. So to put it another way, any separable Banach space embeds isometrically into C01 or C of delta, where delta is a counter set, in the SPR way. Also, any dual Banach space with separable pre-dual embeds isometrically into L infinity in the SPR way. So L infinity, for instance, will embed into itself in the SPR manner. So once again, you can embed every separable Banach space into L infinity in the SPR manner. So those Banach spaces such as C01, they're fairly rich. Of course, there are, in a sense, smaller C of K spaces. So the question is which of them have SPR subspaces. So it turns out that a space C of K has an infinite dimensional SPR subspace if and only if K has infinitely many accumulation points. And if K has infinitely many accumulation points, then it turns out that C0 can be embedded into this C of K as an SPR subspace. And maybe finally, I want to mention some results about the stability of stable phase retrieval. So first of all, we have the stability under closure. So a subspace does see stable phase retrieval if and only if its closure does. This is, by the way, not true for the usual phase retrieval. Phase retrieval is very fragile. It can be destroyed simply by taking the closure of a subspace. We also have stability under small perturbations. So this is somewhat related to the so-called gap metric, which was at some point in the 90s extremely studied by Nigel Carlton and by Michael Ostrovsky. So let's say that E does see stable phase retrieval. Let's say delta is a sufficiently small positive number. And let's say F is another subspace of X, so that for any X in the sphere of F, you can find X prime in E, which differs from x by less than delta. So in other words, f is, well, as is f is another subspace of x, which is sufficiently close to E. Then it turns out that f does SPR with a constant C prime, and so here is this estimate for C prime. And finally, I want to say that we have also stability under ultra product. So if we have a set I, capital I, for any little I in capital I, EI does C stable phase retrieval in Xi. And then if we take an ultra filter, you take an ultra product, you take an ultra product of Xi's. Well, we know that an ultra product of Banach lattices is once again a Banach lattice, and the ultra product of subspaces still does the C stable phase retrieval in this ultra product Banach lattice. This I started my talk with pictures, so let me also end it with pictures. So this bizarre thing is actually the one of the first photos of the X-ray diffraction on the DNA. So this, I mean, you look at this and you see almost like those X-fighters from Star Wars movies. But apparently from this, they could deduce the double helix structure of the DNA. And this is Rosalind Franklin, who actually took this image. Unfortunately, she didn't live long enough to receive her well-deserved Nobel Prize. So I guess I should wish everybody to live long, happy lives, maybe not collecting Nobel Prizes, but still enjoying life. And thank you for your attention, and thank you for coming, although in a virtual manner.
Yeah. So thank you very much for a very interesting talk, and we wish you success today, that all your local plans will be fulfilled, and forever. Yes, and forever. Yes. So, does somebody has questions to our speaker?
Yes, I have. Yes, thanks for interesting talk. Well, I have a question concerning if you start to classify subspace of the measure space with SPR, eventually it's going to reduce to a subspace of the lattice ideal, right? Generated by some mu measure, and measure should be sort of scattered, right?
Well, I'm not sure what you mean.
So, for example, get a compact space, a Hausdorff space, and get the measure space, not C, measure space, and suppose you wish to classify subspaces of this with SPR.
You mean like measure space, and you mean like the space of measure on like the dual of
yes, all measures, yes, the dual space.
Okay.
But this also Banach lattice, right? So you're going to start to classify.
Yeah.
Well, it seems due to the composable properties, probably it's going to reduce to ideal, right? Generated by some measure mu, and mu should be sort of scattered. Am I right? So do you have sort of classification like that?
So I guess it depends. Let's see. If the measure mu is scattered, so if, let me put it this way. So if we have something, if the measure mu were purely atomic, then there would be no SPR subspaces.
Yeah,
because if you have something purely atomic, then you can run the gliding hump argument.
Yeah, that's right. But first
However,
step is correct, right? First step, it should belong to some ideal, is it? Lattice ideal.
it should, well, I mean, it's,
Because otherwise you can get something.
I'm not certain,
I
because
see.
you see, like of course it's the whole lattice is the lattice ideal. But whether you can
I mean the
somehow
crystal
make,
one to some mu. So because otherwise you may have something like disjoint stuff, and it can occur in this subspace, but I'm not sure again. Yeah.
I mean, I honestly I have not looked at that. So let me say this. Of course, the space of measures is an L1 space for some weird measure.
No, it's a sum of L1s. Like it looks like you're embedding like sum of L1s, because there are lots of measures, there are lots of decomposition there.
Yeah, but now it's an L1 sum of L1s.
Yes, L1 sum of L1s. Yeah, yes,
Right.
that's right.
Right.
Okay, yes. But anyway, there are lots of the disjoint stuff, right? So you should escape them all by somehow.
Well, you should. So I guess I'll have to focus on. Yeah. So yeah. Okay. Now I understand. So yeah. So there will be. So then you can only cover countably many of them. Yes, so in this sense, yeah, it will be some kind of an ideal, and with a scattered measure. Yeah, I believe that this will be true.
But there must be something more again, more deeper. If you shoot down, if you move to bottom, there must be something else there as well, right? It may not be enough yet.
I'm not sure, because okay, so you essentially so you can get to the point where you have some kind of capital L1,
Yes.
which is non-separable but still with a dispersed measure. So if you look at separable subspaces, separable SPR subspaces, then you just get whatever you get from the usual capital L1. But if you see what happens in general, then it's somehow like honestly, we have not looked at non-separable SPR subspaces, and they will undoubtedly occur there, or they may well occur there, and I honestly don't know what they will look like.
I see.
So far we've been sticking to LP01 because this is kind of a nice model.
Yes, yeah, that's right. Okay. Yeah, thanks.
Okay.
Yeah, thanks. It's all fine.
Other questions? Yeah. So yes. Okay. So let's thank again our speaker, and we meet next week, I suppose. So, where the lady who